Yeah, g'day, it's Charlie ZL2CTM. Well, I just want to cover off today looking at what I've notionally called the VFO, which is this part here, and the Si5351. And then on the second part of the video, just look at the calibration of that Si5351. So what you'll see here, in the spirit of keeping this first version of this radio nice and simple, I'm just going to use that 2-line LCD display. Once the radio is all built and documented, then I will actually go back into the code again and then support a much larger screen with fancier graphics, so to speak. But like I say, in the spirit of keeping this initial version cheap and cheerful, I'm going to use this display here. So anyway, in terms of how it's set up, rotary encoder, of course, changing the frequency there. This top right hand side is the radix, in other words 1000 Hertz or 1 kilohertz. That 4 will be increasing, so that 4th digit there. This bottom little momentary switch here just cycles through the various radixes that I've got built in, so 1000 to 1 kilohertz, 100 Hertz, 10, down to 1 Hertz, and then back around again. So you can select whatever you like, and then that will be the step in which the frequency will change. This top switch here is the upper sideband and lower sideband. It's in the down position, so it's the lower sideband. In the upper position, it's the upper sideband. Right hand side will be, excuse me, the volume control on receive, and then that'll be the microphone. So just spinning it around. Oh, geez, excuse me. Let me just spin it around, and we can have a look at the back of it, and then I'll go through the wiring schematic. So I'm going to keep it on this copper board for now, and once I've got the whole thing built up, then I'll look to put it into a nice box. So hopefully you'll be able to see two things at once. This is the schematic, very simple for this part of the radio. Right hand side here is the Arduino. We've got our digital pins here, and our I2C, the SDA and the SCA, the data and the clock. So starting at the top, no particular order, we have the rotary encoder. Its configuration needs to have two 470 ohm resistors on the output, then a couple of 10 nanofarad capacitors to earth. That's an arrangement there. That radix switch, that momentary switch, that is switching in earth to pin 4. It's a momentary switch, that's this one here. And then we have our upper band and lower sideband switch. That is not a momentary one, that's in the permanent. For upper sideband, it's not providing an earth, and lower sideband it is. A poor way of saying it. So it's looking to see if there's a 0 on that particular line there. And the two I2C devices, our screen here and our Si5351. The SDA and the SCL lines, as you can see there, are paralleled up. And the Arduino knows which one to talk to via the address. And that's it, and basically just hanging off the 5-volt line, which is sitting here. So that the way it's going to be working, I'm going to have 13.8 volts on the radio, so I'm going to use that, assuming that I don't have a noise issue. I'll use that laptop power supply to provide the HT, so to speak, the high tension or the high voltage line, mainly for the RF amplifier. I'll run that through a voltage regulator, drop that down to 13.8 volts, which will run things like the audio frequency amplifier, the microphone amplifier, and the IF amps. And then another regulator here, it's a 7805, a 5-volt regulator, which is then dropping that 13.8 volts, which is not wired up yet, down to the required 5 volts to run this portion of the radio. I'm also, as you know in the code, which we'll look at in a sec, I need to know what state the radio is in terms of being in transmit or receive, because the Arduino needs to tell the Si5351 to swap its output between clock 0 and clock 2, depending on transmit and receive. And like I say, I'll show that in a sec when we go through the code. So we need a simple voltage divider here, and I'll just very quickly run through the maths on that one. It's a straightforward. In fact, let's do that right now. So for a voltage divider here, we know that the voltage at the tap point is our overall voltage multiplied by R2 over R1 plus R2. So this expression here, we want to equal 5 volts, because 5 volts is going to be our logic level 1 that the Arduino is going to be looking for to basically say that yes, 13.8 volts transmit is there, or in other words the radio is in transmit. So this is our expression, and what I want to do now is I want to expand this out and make R2 the subject, because I'm going to tell R1 that's going to be a certain value, and then I need to work out what R2 is going to be. We don't want to have two unknowns, we only want to have one unknown. So let's make R2 the subject. So what we can do, we can divide both sides by 13.8, which will get rid of that, which is the same if you do a lot of algebra, it's the same as just moving that from the top line to the bottom line on the other side of the equals. It gives us this. We can then move or multiply, strictly speaking, multiply by both sides by R1 plus R2, and if you do that, this side will disappear, and then we have an R1 plus R2 on the right hand side. In other words, just move it diagonally across the equals to the top half. Divide that out, so 5 divided by 13.8 equals 0.362. We can now multiply out the brackets, so that times that plus that times that, because it's this expression here, because we want to get, eventually we want to get this R2 back across to this side. So what we can do now is we can subtract from both sides the expression 0.362 times R2, which will remove it from this side and put over here. And then we can, and excuse the algebra, but you know, people want to see what the maths is, so we might as well go through each of the steps and see what we come out with. We can now see that we have two values of R1, so let's put R1 outside of our brackets and have 1 plus, or 1 say again, minus 0.362. So in other words, if you would expand this out, you'd come back to here. So we're just simplifying the equation here. And now this is not subject to a variable like R1 or R2. So now we can divide both sides by this, which will get rid of it on this side and put over to here. And then finally, after all this, we come out with an expression that R2 equals 0.567 times R1. As I mentioned at the beginning, we're going to set R1 to be a value, and I'm going to use 10 k ohms, and then I just plug 10 k into that, multiply it by that, comes out at 5673. Near a standard value on the lower side is 5.6 k ohms. And why do I say that on the lower side? If I make this slightly smaller than exactly what it's going to be, then this voltage here won't be greater than 5, it'll be less than 5, which is on the safe side for the Arduino. If I'd gone up a standard value, then potentially I could have ended up with say 5.6, 7 or 8, in other words higher than 5 volts. So here I was pretty well spot on, just had to go down to that standard value of 5.6. And you can't quite see it, but that's that little voltage divider sitting in here. The junction is sitting down on digital pin 6 per the diagram. Our 10k is going to be our input, and then that 5.6 goes down to earth. Okay, so taking a look at the software. Now I'm using the inbuilt Windows recording software here, which I've never been able to get the microphone volume loud enough, so I'll try and talk reasonably loud, but I apologise that the audio is probably just a little bit low. But just running through the software just quickly, I won't go in line by line, but just go through the salient points, noting that this is just the interim software, and we won't finalise this until we have such things as the crystal filter built, as an example. Anyway, so first part of the sketch, or the code or the program, is just loading up the two libraries, one for the display, one for the Si5351. Just a reminder, I'm using the EtherKit library, which has worked well for me in the past. At the moment, this is set for 80 meters, so we just got our two band extremities there, and our start frequency. I'll just highlight these two here. The lower side band VFO frequency and the upper side band VFO frequency. Those two frequencies there are just notional, and like I say, we won't be able to finalize those until such time as the crystal filter is built, and we test it and work out where those two frequencies need to be placed in order to get our best reception. So like I say, notional software at this stage. Just carrying on through, initiating or instantiating the two objects, one for the display, one for the Si5351, that is. The setup here, just setting up the I/O pins. In this case, they're all inputs, and just making it that where required the pull-up resistor is enabled. Just initializing the display and initializing the DDS. Now, just noting there the correction factor there, 62,100. You'll see just after this part of the video, I've tacked on the calibration for the Si5351, and you'll see that calibration came out with a calibration factor of 62,100. So that's where that comes from. Now the main loop itself is very simple. It's just checking to see if the rotary encoder has been manipulated. I'm just using the software that was provided with that particular rotary encoder. Checking the radix switch to see if that's been toggled, checking the mode switch just to see if that's changed, and then also checking the PTT. In other words, are we in transmit or are we in receive? So they're just calling sub-functions, which we'll just nip through now. So first one, checking the encoder. Again, just reading the 2 pins associated with that, just to see if we're going anti-clockwise, and if we are, to decrement the frequency, or if we're going clockwise to increment our frequency by the radix. Noting that if we get to the 2 extremities of the band, we won't go any further. So the band start and the band end. If something has changed, in other words the frequency, we want to update the display to make sure it's actually displaying the correct frequency. Send that frequency to the Si5351, and that's all. That second function, checking the radix switch, much the same, just reading the switch, and if it has been toggled, decrementing the radix by a factor of 10, and if it tries to roll below 0, it just rolls back up to 1000. So as we saw in the very first part of the video. If that has changed, we just update a second portion of the display update, which I'll talk about later. We don't need to change any frequencies because we actually haven't rotated at that point in time the rotary encoder. Mode switch, just reading the mode switch. If it's been earthed, in other words, it'll read it as a 0, it's lower sideband, and if it's open, the pull-up resistor will pull it high, and it's read as a 1 or upper sideband. If that is the case, we'll need to update the display so it's reading correctly, and we also do need to change the send frequency, because we'll need to change the VFO frequency between the upper and lower sideband frequencies as required. Check PTT pin, this is the one that's reading the voltage divider. If it's a logic level 1 or 5 volts, it determines that it's actually transmitting. It'll then update the display. It'll also send the frequency, because we'll need to toggle the clock 0 and clock 2 outputs, which we'll see in a sec. And that's it. Right, so near the end now, so just 2 functions for updating the display. I did have one function which did everything, but I noticed that when I was changing frequency, the radix was just starting to flicker a little bit, which annoyed me. So I pulled the radix display portion out into its own function, and only updates if the radix is being updated. Otherwise, all the other parts, for example, upper sideband, lower sideband, the transmit receive, get updated every time, for example, the frequency changes. Which brings us to the last part, which is the send frequency. This is the one that sends the command to the Si5351. Essentially 2 parts to this, depending if it's on lower sideband or upper sideband, and then within those 2 parts, are we transmitting or are we receiving? And as you'll see there, the difference at the macro level, which is the lower sideband versus upper sideband, is the use of the lower sideband versus the upper sideband VFO frequencies. And then within those, if we're transmitting, we have, for example, in this particular case, the VFO coming out on clock 2 and the BFO coming out on clock 0. And if we're on receive, that gets inverted. So you just see there, what was a 2 becomes a 0, and what was a 0 becomes a 2. And that's basically it. That's all that changes. And that's it. So same logic for the upper sideband. So that's all I'm going to talk about for this. Again, apologies that the volume was a bit low. Turn it back down again, because the next part of this video will be looking at the calibration of the Si5351. Okay, so as I just said, I'm going to now calibrate the Si5351 and then put that calibration factor back into the software build, so I know that this particular Si5351 is going to be about the right frequency that I'm after. It's pretty well the standard temperature here, so all things being equal, we can go ahead now and calibrate that particular Si5351. So on the left hand side I've got the sketch. Now the sketch came from Tools, Examples. The library I'm using is the Ethernet or EtherKit library, Si5351, and then the sketch I've loaded into the Arduino is this Si5351 calibration. That's what we see there. I've uploaded that, and then I've opened up the serial monitor page, and we can see the commands there that we'll be using to increase and decrease the frequency by these ratios here, 10, 100, 1 kilohertz, 10 kilohertz, etc. And the whole idea of by increasing in those and decreasing those is to eventually make the Si5351 output exactly 10 megahertz. Now, as I've done in the past, I'm going to do it again now. I'm going to use a general coverage receiver here set for 10 megahertz. In fact, just slightly off, so I get the tone coming through from the CW signal here, and I'm going to beat that Si5351 10 meg signal with the output of my SIGGEN. I'm pretty confident that the frequency out of this is good enough for where I need to be. So I've set this for 10 megahertz, and I've set the amplitude to be such that when I detect the output of this on the receiver, its amplitude from an audio point of view is about the same as what I'm hearing directly from the Si5351. So one is not swamping the other, so to speak. So if I was to go back to the receiver here, I can turn that on, and at the moment the SIGGEN is off, so all I'm detecting there is the output of the Si5351. And if I was now to turn on the SIGGEN, we hear another tone, and clearly the two tones are not the same, so which tells me straight away that the Si5351 is not outputting exactly 10 megs. So we're going to beat this, and you'll hear the beat frequency coming in shortly. So let me just go back up to the sketch here, and more importantly, let's just concentrate on the right hand side. I won't zoom up too much more, but it should be enough to just get an idea of what's going on. And what I'm going to have to do now is I'm going to force the output of the Si5351 to change its frequency by using these commands here. So let's start off with K, which should be increasing the frequency by 100 Hertz. So if we go, make sure my mouse is sitting up in this little box here. It is. And let's just try that. K, enter. We hear it increasing in frequency there. We'll try another one. Getting closer. Now the beat, we start to hear that beat coming in now, getting close. And it's gone too fast. Let's go back down again. So above K is I, and that decreases it by 100 Hertz. So I'm going to start here at, don't worry about this number here, this is the number that we'll be eventually throwing into the Si5351. All I'm concentrating on here is the sound. You can just hear that beat frequency. So let's try fine-tuning that. So rather than using 100 Hertz, let's try using 10 Hertz, which is the U and the J key. Let's try J. Getting close, let's try one more. We've gone out the other side now, so the beat frequency is increased. Let's just go to U and go back down one. Getting pretty close there. So let's now try changing at 1 Hertz at a time, which is the Y. So again, we'll try, Y and the H. Let's try that. Y and H. Starting to hear the old beat there, so I'm going to go back the other way. We'll go through it and go to the other side again. Yeah, there goes the beat coming back again. So it's there, it's well under a hertz. So if I wanted to now, we could use the T and the G to go by 0.1 of a hertz. But I don't know about you, but that's pretty close for what I'm happy with at this stage. There's ever so slight beat there, but it's, you know, it takes several seconds, so, you know, it's well under a hertz. So I think at this stage I'll lock into that. So that number there now, 62,100, is what I'll be then loading back into the main software. So when I put the software up on the blog and you see that number, that's where it came from. Okay, let's keep going.